don't tell anybody. That's what you get for showing up tonight. All right, let's see. I'm going to go back through the chat and wait, what? What? Did you just sign in? Yeah, problem 40 I did in class. 29. Oh no, I never delete a problem, but I do make a mistake once in a while. And that's what happened there. Oh, I could put in another problem if that's what you'd like. I don't think so. I didn't think so. All right, so how about if we start with 629 and then we'll do 610 and then we'll do 632. That sound like a plan? Okay, so we have incompressible two-dimensional flow, non-viscous fluid, and we have a velocity potential. And what we need is to determine the corresponding stream function. So basically, we want to know what this is. And we want to know what this is between the walls and the coordinates. So notice when they're saying, well, we'll get to that when we talk about Q. So in order for us to find the stream functions, what do we have to find first? Right, the trident. Yeah, that's better, I guess, than a pitchfork. So before we find the trident, we do have to find U and V. So we know that U is equal to D trident. I'm going to use that from now on. And V is equal to this. However, U is also equal, and this one I know, d phi dx. So what is d phi dx? And hopefully that's something that, yes. So d phi dx is equal to x, and d phi dy, or 2x, is equal to what? Minus 2y. All right, so now that we have U and V, now we can find, this actually should be like, this actually should be like this. The integral of this, and so this is going to be 2x what? And I guess when I'm, be careful there, and that's exactly why I said that. Take a look here, okay? So 2x is our U. If we're now looking at the stream function, and exactly, when we separate and integrate here, what we're saying, and then maybe I skipped a step. So what we're saying is that this is equal to 2x, and so if we separate and integrate, I did that wrong, this is going to be equal to 2x d, that's not what it's supposed to be, dy, okay? And so now we can integrate this, and we find that this is equal to 2xy plus what? Plus some function of x. And now we do the same thing here. So, but remember, this is negative is equal to negative, oh, how nice. They drop out. And so this is equal to 2y dx. And so what does that mean that this is equal to? Yeah. Now be careful here, and I see why you're doing it. This is 2y dx. So it's 2xy plus some function of y. So if we were to put these together, what would we say that the stream function was? That's exactly it. So that's equal to 2xy, actually, 2xy plus a constant. Exactly. Very good. You guys didn't add it together. You just put the 2xy. So let's take a look at part B. And by the way, one of the things that you can see, take a look at this picture right here. So it says that at y equals 0, we know that the stream function is equal to 0. So we can say here that our constant can be equal to 0 here. So let's find the second part of the problem. Probably the harder one. So what is the relationship between the discharge? I don't know why they call that, I call it flow rate per unit width normal to the plane of the paper. And that's something, again, that you need to get used to, that W, if you want to call it that, is one, whatever the unit is, normal or in the back of the wall. Passing between the walls and the coordinates on any point of the curved wall. And so if you remember from class, what we said was that Q is equal to the second stream function minus the first stream function. So, or A minus B, whatever. What's the first one of the first stream functions equal to? It says it in the picture. Yeah. So this is minus 0. What's the second stream function equal to? I will go like this. We know that this is minus 0. 2xy. But we have to be very careful because what it says is the coordinates x sub I and y sub I. So this is equal to 2x sub I. And this makes it so that it is any point on the curved wall. So what we're really looking for is any one of these points here. Minus 0 or just 2xi, yi. Okay? Okay, I'll look for 2. I'll check the textbook answers, okay? So when you say I agree, what do you mean you agree? You agree with the question or you agree that the textbook answers are wrong? The signs are messed up. So that is for, what'd you say, 6.8 and I got this one, 6.24. I will definitely check them and let the TAs know. Oh, I can see right away with 6.24. Did they have a negative in the back? I guess I'll check. I think it is supposed to be negative, but we can go over that while we're going over the rest of these. The long term is positive and the short one is negative. Let me finish up this and then I'll come back to that one, okay? So somebody asked me way back, how did I get this? Well, if we go back to what our stream function is, it's right there. But what we need is any point on the curved wall. And that's why we get x sub I and y sub I. So for our x, we put in x sub I, and for our y, we put in y sub I. Does that help? No, I didn't differentiate. So it goes back to what the definition is. We know what the stream function is here. It tells us it's 0. The other stream function here, which is based on the velocity potential right here, x squared minus y squared. Oh, how did I differentiate psi 2 from psi 1? I actually took the one that was higher. And if you look at Q, all right, I can tell you actually exactly why. Notice, right, that Q is going in the positive direction. And the only way that Q can go in the positive direction is if one is greater than the other. So we know that 2xiyi is going to be greater than 0. Does that make sense? Okay. If it were backwards, oh, that's a great problem. If it were backwards and then it would be equal to, let's say Q was negative, going in the negative direction, then it would be 0 minus 2xiyi. Put this in my notes. All right. Other questions? Want to go on? Where should I go next? I think somebody asked for 10. Want to do 10? Oh, why not? I actually thought this was the one that was going to be the hardest here. So we have a viscous fluid, you did small rectangular element, determine the rate of change of the right angle due to the fluid motion. Okay, so what is another name for the rate of change of the right of an angle? There's another name for it. I know you see the viscous part, but there's actually another part of it. And we only mentioned it briefly, and I probably should have talked about it more. All right. So yeah, we have that gamma, and it's actually gamma. And what's it equal to? Angular deformation. That's exactly right. So this is equal to dv dx plus du dy. And if you notice the difference between this and rotation, what is the difference? First of all, what kind of derivatives are these? Yeah, these are cross mix whatever derivatives. That's exactly right. So, but what's the difference between this and rotation? Yeah, exactly. It's positive versus negative. Okay, so what we need is dv dx plus du dy. Now, what of these is equal to 0? Which one? Yeah, dv dx is equal to 0 because if you see the axes right here, that'll tell you that. So what we need now is to find a u. And so what does it say that helps us find that u? There's a particular word in there. That's exactly right. This is linear. So we're going to do what we've always done before. Is the first thing we're going to do is we're going to say that, sorry, u is equal to some a y plus b. All right. So the first thing we do is we look at, and we should get used to this because we're going to be doing this starting tomorrow. And I just put up the homework, and they're probably, it will be up on Wednesday, 4 or 5 problems using boundary conditions. So let's learn how to use them right now. And so what that means is at some y equals something, u equals something. So give me an example here. I'll start right now. So dv dx and du dy, when you say the relationship, if you remember when we were looking at that, remember this? And we had an angle that was going like this and an angle that was going like that. That was angular deformation. And one was in the x direction with respect to b, and the other was in the y. All right, so at y equals ri, all right, and it says there, the inner wall is fixed, u equals 0. So we have to find both a and b. So now we have to find something else. So at y equals what? Where else do we have a boundary? Right, at y equals r0, what does u equal? Be careful there. And I know you mean omega, right? But take a look at the picture. Which direction is it? And negative, that's exactly right. So there, u equals negative omega r sub 0. And so when we put these into our equations right here, and this is something that's you should take a look at because it makes your life a lot easier. So we know that a equal or 0 equals a times ri plus b, and we know that omega r0 equals a r0 plus b. How are we going to get rid of that b? You have to be careful though, because we got to get rid of a as well. We could add the equations, or even better, b does equal 0. We don't have to solve for b. We don't have to go b over a. Let's make it really easy on ourselves. And whoever said add them was really, really close. So you can set them equal to b and then set them equal to each other. You can do that, or, and I like that. So basically, you're saying that b equals minus a ri, b equals a minus a r0 minus wr0, and then you can set these equal to each other and we don't have to worry about b. The other thing we can do is take these, oh that's a mess, and take equation 2, equation 1, and subtract 2 minus 1, and that gets rid of 0. I mean, sorry, that gets rid of b. And so what that does is it allows us to solve for a. So what we have here equals a, which is exactly like you were doing before, r in outside minus r inside. So our a is equal to this, and therefore our u is equal to minus omega Ri. Is that R0? That's R0. R0 minus Ri times y. We could also change this to omega R0 Ri minus R0. But if you notice, what does that mean about the velocity? It's negative. That's all I wanted. All right. So what do we want? Let's go back to what it is that we want. We need this, which is equal to du dy. What? Oh, actually, b is 0. So what we did, and actually, if you want, you can go back and find what b is, but you'll find literally the best way to do it. So b equals minus Ra times Ri, and then when you put a in times Ri, I'll have to check that out. We solved each for b and right. So what we did is we're disregarding b, okay? And because we're all looking for is that a. So what's our du dy? Pretty simple. I won't even ask you because it's hard to write. R0 minus Ri. And I think that's all that they're looking for. And so what that means is that we, what does it mean about the angle? If it's, no, it's decreasing, it's getting smaller. So the thing is, you're saying if it's positive, it's decreasing. That's absolutely right. No, if it's negative, it's decreasing. So if it were positive, it would be going, and note what they say, rate of change of the right angle due to the fluid motion. And because it's negative, it means that it's decreasing. Does that make sense? So you're already starting with a right angle. No, it's not increasing. Oh, whoa, 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 whoa. Let me take a look at this. So the negative sign indicates that the original right angle is increasing. And the reason for that, sorry about that. What is the reason for that? Why is it increasing? And you're absolutely right. What is it about the velocity profile? Or why is it increasing? Let's put it that way. So it's linear, but why? Here, let's start and look at this one. What's the sign of our rate of change of the right angle? Negative. So which way is it going? It's going in the negative direction. Okay? Okay, so we're going to start here with this angle here. And so we have this angle that we're calling, what are they calling? Oh, here. And what's happening is that the rate is in the negative direction. So if the rate is in the negative direction, that means it's going that way, right? Because that's negative, which means the angle is increasing. Does that make sense? Okay, and if it were positive, then we'd start like this, and then it'd be in this direction, so now it's decreasing. Okay, where would you like to go next? Nowhere? I can go to dinner. Nope, I'm not going to do 640. So why am I not going to do 640? Normally I'd be like, oh, no problem, happy to do that. Yeah, we did it in class. Sadly, I did not check that, but you should be happy that you have a better idea of it. All right, let's do 632. Not sure how to do the assumption. All right, so what are our normal assumptions for Bernoulli? And this is actually a really good question. And you can do it in shorthand or whatever. What assumptions do we have? Inviscid, okay. Incompressible, okay. Steady state, and here's the difference. Now, and wow, you got them all in, great. Instead of a streamline, now we can say, because we're looking between any 2 points, so not along a streamline, but anywhere. So what does that mean the flow has to be in order for it to be applied between any 2 points? Exactly. So now what we find is if it's irrotational, we can put it between any 2 points. But if it's not irrotational, it is. If it's not irrotational, what it means is then it has to be along a streamline. So how do we find if it's irrotational or not? No, we assume, notice it says incompressible, 2-dimensional. I would say that you don't have to worry about inviscid, because if you notice with the problems here, oh, I'm on a totally different problem. If you notice, if it's viscous, then, it says that it has viscous forces. In terms of whether it's steady state, what would have to be in there in order for it not to be steady state? Exactly. So we know that. We know about the inviscid because it would say viscous fluid. How about the incompressible? How could we find that if it were incompressible? How? Or, yeah, well, let's do it easier than that. And this is 2-dimensional. Okay, so we can, nice spelling, you're worse than I am. So we can do that, but let's do easier. du dx plus, which is the volume, dv dy equals 0. And we can also just say that this is continuity. And so if it equals 0, then it's incompressible. Okay? But we don't need to, I'm just laughing because you've seen the way that I write words. We can find the vorticity, but we also just can find the rotation. So how do we find the rotation? What does it have to equal? And I think somebody was close to this. We said for it to be incompressible, this has to equal 0. That, exactly. So del cross, and that's why we call them cross derivatives, equals 0. And so what that means is dv dx minus du dy equals 0. And do you remember why it's minus? And I'll go back to this. Remember we had this angle here, and this was positive, and so to rotate, to continue that, then it has to be negative. Yeah, it's the counterclockwise versus clockwise. Or the rotation, actually the rotation versus deformation. Both of them are exactly right. So dv dx minus du dy equals 0. What do we have to find? Yeah, so basically it's just that u is equal to d, what did you call it? Trident, dy, v equals minus dx. So what you do is you can find du, this right here, and you can also make sure that it is incompressible. And so although they don't say that apply any 2 points, they don't say that it's incompressible. So you also have to use continuity. Otherwise you won't get full credit. So use, we could say vorticity, because that's really what it is, as well as continuity. So does that help with the assumptions that we make? Okay. All right, any other questions that people have? I would say that this was a relatively, okay, I'll come back to that. Straightforward homework. I will give you a heads up that the next homework will take, it's not like lengthy, but it will take some thought. So, no, I didn't look at it yet. Oh, how exciting. I'm responding to everybody. Why do we need to do vorticity and continuity? And that's actually a really good question. So doing continuity says that the fluid is incompressible, which is one of the things you have to have. Doing vorticity says that it is irrotational, and here it goes a little bit further, because what that says is any 2 points. If I didn't ask for any 2 points, then your assumption would be along a streamline, okay? But if you do irrotational, and I'm asking between any 2 points, then you can use it. In terms of steady state, we already showed that it is not a function of t. And in terms of inviscid, it doesn't say that it's a viscous fluid. And you can assume that it's not viscous unless told. So now I can go back to the 2 that had the sign problem. Which ones were those? Eight. So let's take a look and start with 8 here. For a certain the velocity component, so what do we know du dv dy, so du dx equals minus blah, blah, blah. So what does it say in the back, and 24. So what does it say in the back that the signs are? Negative or positive for number 8? Negative, positive, positive. What does that mean? So you should have u equals some term plus some term plus some function of y, I guess it is. Okay? So the second and the third are positive. Okay, minus 3 to x squared plus, yes, the second one should be negative. And you know, it's interesting because I'm looking at my notes and it said that it was positive and I crossed it out and it's negative. Okay? And we grade it from my notes. All right, let's take a look now at 24. Corresponding tangential velocity component required to do. So both of them are negative, exactly. All right. Oh, wait, so this equals negative, and so this equals negative. So what does for 624, what does the answer say? And you are claiming that it should be 9r squared thing be positive. So why is it positive? I'm looking at this and it should be positive. I think what happened is when they took the integral of the sine of theta, they probably made it the cosine of theta, and what should it actually be? Yeah, it should be actually minus cosine of theta. So you're right, the signs are wrong on that. So the bottom line, no, yeah, I guess they do, is that you at least seem to know your stuff here because you wouldn't be able to catch that they were negative. So I see that people are starting to drop off. Are there any other questions that people have? I expect hopefully next Monday to have a huge crowd. Have I uploaded my notes? I thought I did it for both 16 and 17. Does anybody know? Because I thought I did that last week. I would go and check, but if I go on to that, then I'll lose everybody. I'll tell you what, I will check and make sure that I've uploaded them, and if I haven't, I'll do them right after this. Okay, that'd be great. So any other questions while I'm here? I can talk about lots of things, art history, anything you'd like. You're very welcome. What's my favorite color? Yellow. The last one is class 15. I will go right now when we're done and load the other ones, okay? All right, well, I'm going to say goodnight to everybody. I'll see you all. You're welcome. I will pay a good dinner. And I'll see everybody tomorrow.